the chair of math department and all of the audience to be here. Yeah. Actually, the title is the weak Northcott's property and D ratio of rational maps, but I didn't have much space there, so there's the reduced title, D rationalist applications. Yeah. I should start with the theorem made by Northcott. In 1950, Northcott proved some relation between height of point and its image by morphisms. If we have morphism projective space, and we made quite a good inequality between height of points and height of images, like this. Actually, yeah, I will explain what the height is. Yeah. Actually, this height inequality comes from some functorial property of Weil height machine, which makes the relation between the Picard groups and height functions given on given projective varieties. So this inequality is quite useful. For example, if you have elliptic curve or abelian varieties, this inequality actually gives you canonical height function, which is built by the Tate, Narrowman-Tate. Unfortunately, it only works for morphisms. If you do not have morphism, for example, we have rational map on surface or other big spaces, then functoriality of the Weil height machine fails. For example, we might have some sub-variety Y, which is reduced to 1 point by your rational maps. So on previous pages, your images say point, so there's a constant while your height of point goes to infinity. So this inequality is quite invalid for rational map cases. For example, let me assume we have polynomial map on the affine spaces, like we have map which send x to x squared and y to y cubed, then we have some problems. So we will consider another ones. Previously, we make inequality with some degree conditions. Now we will do out the conditions, but we just expect we might find some constant which makes the height bound of point by some multiple height of images if we exclude some close-up variety where your rational map acts quite bad. To explain what happens on the morphism case, we should check what's the definition of degree there. Actually, we usually define the morphism's degree is the field extension degree between function fields. However, geometrically, if we have morphism projective space, we might define the degree, which is a constant comes from the linear operator, which is defined on Picard group induced by given morphisms. So we have some picture like this. Let me assume we have quite a trivial birational map from Pn to Pn. Then we have map phi and identity maps. Now we want to compare two products made by your morphism and identity maps. Then they compare these two coefficients made by these two products. Then we have coefficient like degree and number 1, whose ratio 1 over degree from phi, which makes inequality on first pages. So we want to check it like that. If we have rational map, then consider some kind of resolution of indeterminacy, which provides some two morphisms induced by one rational maps. Now we want to compare what's the proven made by these two morphisms, which have the new projective variety, and we want to compare them to induce the weak Northcott's property between height of point and its images. So that's the big picture. If we have two products like this, we are not going to claim we have minimum ratio between these two coefficients, and that's the constant which makes Northcott's property for your rational map. But clearly, I'm sorry. For notational convenience, instead of minimum bi over ai's, actually I just define like this. Our D ratio may be degree times maximum ratio of coefficient which has two product graphs. Oops. Yeah. Actually, I skipped lots of things. I didn't explain what's the height is and what's the birational map happens there. So I just give you brief pictures here. First one, if we have rational map, that's the fatal errors if we make a Bay height function machines. Bay height machine allows only morphism to make functional reality. So first one is we should build some morphisms which works well in your Picard groups and Bay height machines. So we use some theory from ASARC geometry, which is called resolution of singularity, which makes if you have singular varieties, then we have a birational map, which makes a birational map from non-singular variety to singular varieties, which has corollary, which is called resolution of indeterminacy, which says if we have rational map between two proper varieties, then we have birational map from non-singular variety, where composition of your birational map and rational map becomes morphism between two projective varieties. So instead of observing your one rational map, we will observe these two morphisms, which works on your Bay height machine, which generate height functions. So for notational convenience, I just say if we have pair variety and birational map, then we call this resolution of indeterminacy of some rational map. If we have previous picture like this, now we have y and x, and we have rational map here. Now if we have a projective variety with birational map pi, and their composition becomes a morphism, then we say this pair as resolution of indeterminacy of f, and we call this inducing morphism as resolved morphisms. And instead of f, we compare phi and pi to make height functions. Okay, here's some clear ones. If we have global Pn, then we have Picard group as pre-Z modules. So we can easily generate your Picard group with some Z modules. So we might express your divisor and your projective variety as sum of some exceptional divisor and then exceptional parts. And that's the exercise of Harshas. So we might express your Picard group is just Z module generated by generally your Picard of Pn's and some multiples of exceptional parts of V. Now, I will explain why we require two observational Picard groups there. We have height function, which is defined in projective space, which gives you some arithmetic complexity of real numbers. For example, if we have some integers, we might check how complex your number is as some factorizations of your numbers, which means we want to check how many primes are required and how big primes are required to represent your numbers. So if you have points in project space, we want to check how much primes are required to represent your numbers, and we check how big your number is by observing your Archimedean parts. That's the multiplicative height function on project space over number field case. But it's not enough because we have lots of number fields. For example, if you have number 2, that will include some rational field and Q of square root 2 and so on. Then this multiplicative height of project space over number k varies up to your choice of field. So we should normalize this, which makes it like that. Then that's a well-defined function in projective space over algebraic closure of your number field. Now we have height function, which is well-defined on algebraic closure, and it has quite good property, which is called finiteness. If we have a set of numbers whose height is bounded, then we only expect finite to many k rational points. But it's not enough because we only define your height function on projective space, and we require height function on some projective variety because even we start with projective space like this, we should have some resolution of indeterminacy with your rational map. So we observe everything happens in your projective variety. So we should extend this notion to projective varieties. The idea is simple, because we just say projective variety, which is a closed subset of projective space. So if we consider your projective variety as a closed subset of projective space, then we might have inclusion of your projective variety into projective spaces. Once we have such inclusions, then we might define height function defined on your projective variety, which depending on your closed embedding, then just send your point to projective space and measure its height in projective space, then that's the height functions. Problem is, we might have lots of inclusions. So we need some facts from algebraic varieties. First one, if you have variable divisor, that is one-to-one correspondence with your closed embeddings. So if you have one closed embedding, if and only if you have variable divisor on your projective varieties. So you can define your height function corresponding to variable divisors. Secondly, if you have any divisor on projective variety, then that divisor is linearly equivalent to a difference of two variable divisors. And here's one more thing. Just let me say we have two height functions. Just let me say we have two functions defined on projective variety, which is just a real value function. Just let me say these two functions are equivalent if their difference is bounded by some functions. I mean constants. Which facts generate the very height machine? We have a group homomorphism between divisor V2 height function, I mean the real value functions on V, which satisfies actually your height function, absolute height function defined on previous pages is actually generated by your Bay height machine. Secondly, that's actually they are defined on Picard groups, because if we have two linear equivalent divisors, they will generate equivalent height functions. So we might change it like this. We have a group homomorphism from Picard group to equivalence class of height functions, which is group homomorphism. More clearly, if you have D plus E in Picard group, they will generate by sum of two height functions corresponding to each divisors. So your height function says your height is only depending on corresponding divisors, actually linearly equivalent class of your divisors. So to compare height generated by your image and your point is calculated like this. We have functorial property, so it goes to if we have generated Picard group PNs, that we compare. This one is now generated like this. So comparison of these two height of point and height of image, this one comes from comparison between these two pullback divisors. So first one, we need two pullback divisors, and second one, we observe what's the Picard group of your blow-ups, so we are ready to compare these two divisors. That's the basic picture of my thesis. So, just let me treat it like this. Let me assume we have polynomial map on affine spaces. So we just think that's the dense open subset of projective space. So we have hyperplane, which is complement of your affine space. And we fix that divisor H, and we compare these two, which is probable will fix the hyperplane by these two generated morphisms. And we just assume we have the polynomial maps, so they are well defined on affine space. So they are rational map, which is not defined on some points on your hyperplanes. And we'll just introduce some basics of your Picard groups, which comes from proper transformation of your fixed hyperplane by your bidirectional map, and we say other generator comes from just irreducible components of your exceptional divisor comes from bidirectional map here. Now, previously I just will go so fast, so I might miss it. We have some probability height machine which says if you have height function which corresponding to this effective divisor, which means this linear equivalent to some close-up variety of given projective variety, then they are bounded below on outside of base locus. So using this inequality, we just compare these two by claiming some multiple this one minus this product is effective divisor. So corresponding heights is bounded below on some open sets, and we just claim we have inequality like this. That's the reason why we assume we have basis of Picard group like this. Then we have hyperplanes and some exceptional divisor, which is always defined by outside of affine space. So this inequality holds on affine spaces. So we have polynomial maps that we can define height of point and its image on affine spaces. Problem happens, description of your effective cones. For example, let me say we have a blob up here. Then it has Picard group which might have lots of generators. I mean lots of bases. But if you choose such bases, their base locus might reside inside of affine spaces. Or even we have some non-positive combination of your divisors, it might be effective divisors. So it's quite hard to control what's the effective cone of given blow-ups. So I just introduced another concept, which is I named affine effective divisor. We say if your divisor is affine effective, if your this linear equivalent to non-negative combination of HV and EIs. Which means if this linear equivalent to this divisor, then that's the positive combination of effective divisors. So they are effective divisor. Their base locus only reside in complement of affine spaces. That's the first one why I defined an affine effective divisors. And second one, if we define like this, that's just positive combination of your generators. So it's quite easy to describe, because they are only non-negative combination of given bases. So it looks like, for example, if we have two divisors, then it only says we have first quadrant. Now we just say if D is greater than 0 in such sense, then we say this affine effective, and we say D1 is greater than D2 if D1 minus D2 is affine effective divisor. Then that's effective divisor. If we have affine effective divisor, which is positive combination of our effective divisors, so that's effective divisor. So we might use this property in very height machine. Second one, if we have affine effective divisor, I said that's effective divisor, so that's bounded below outside the base locus. And affine effective divisor is effective divisor whose base locus always reside in outside of affine space, so they are bounded on affine spaces. So that's enough to observe what happens on your polynomial maps. The third one, if we have D1 is greater than D2, D2 is greater than D3, then it's clearly D1 is greater than D3. That only comes from by definition. And it has functional reality. Even we have bidirectional morphism, which makes more bigger and bigger and bigger projective varieties, still affine effectiveness holds. That's because, if we have a resolution of singularity like this, then whatever your bidirectional map is between these two, that's another kinds of resolution of singularity. And we just unify all such cases, so we need functor reality of your affine effective divisors. Now we are ready to define your D ratio for resolved morphism. Just let me say we have just polynomial maps, and we consider that polynomial map is rational map between projective spaces, and choose any arbitrary resolution singularity. Then these two products which reside in Picardo V, so they will represent by their bases. Now we have defined D ratio of your resolved morphism is degree of phi as a rational map on your projective space, and maximum of ratio between your coefficients which happens on your two products. Then it just says like this: your D ratio over degree is a constant which satisfies this constant times product by resolved morphism minus product by your bidirectional map is always affine effective divisors. So that's a divisor which makes your height corresponding to your divisor is bounded below in your affine space, and that's the minimal ones. So that's the minimal constant which makes your weak Northcott property holds in your affine spaces. Here's quite a clear example. If you have a morphism, then your D ratio is always 1 because this one is nothing but degree times h. So that's the minimum number which makes difference of these two as positive combination of h's. So your D ratio is 1 if and only if you have morphisms. Which changes if you have a rational map, then your D ratio over degree of phi, previously you have morphism whose D ratio is 1, so we have previous inequality, and here we have a rational map whose D ratio is greater than 1, so we have inequality like that. Here's one more good fact. Previously I said we just define your D ratio for resolved morphisms, but it only depends on your base rational maps. If you have two resolutional indeterminates of the same map, then the resolved morphism corresponding to each resolutional indeterminates should have the same D ratios. So actually that's the D ratio defined for rational maps, not resolved morphism only. Proof is simple but it's a little complicated. So we need two cases. First one is actually W is the global V. Then we have such features. Then this rho makes functor reality between your affine effective divisors. So proof is not hard. Just we rewrite your combination with new generators which have some bigger blow-ups. So we might compare these two to generate, we have affine effective divisors like D ratio like this. A little complicated, but that's quite a simple algebra. If we have two different morphisms, then we might have bigger blow-ups which contains V and W at the same time. So this resolved morphism has same D ratio of this big resolved morphism, and same thing happens in this pair. So we might claim D ratio is invariant up to your resolution of singularities. So we just define D ratio of rational map for any chosen resolution of the indeterminacy with the resolved morphism phis. we define D ratio like this, then we have some probability of your D ratio. D ratio is always not greater than equals to 1, and D ratio is number 1 if and only if we have morphisms. And if we have composition of two rational maps, then we have inequality between your D ratios. And if we have morphisms, then composition of a morphism just preserves your D ratio of rational maps. For example, let me choose a rational map like this. Actually, that's the rational map which comes from a affine map defined like x squared and y. Then is homogenization says we have such a rational map on P2s. Then we know indeterminate locus is common zeros of your 3 parts. So we only have one indeterminate point, which is just 1 zeros. So if you reserve indeterminates of this function, actually we should blow along your corresponding idea, which is named indeterminate subschema of your functions. If you blow along these ideas, then you need 2 blow-ups. First, I might have picture on the next page. First, just blow along your point P, then we have proper transformation of H and exception divisor, which made by blow along P. Now, blow along these intersections, then we have picture like this. Then this result, after 2 successive blow-ups, that's the variety which makes your extension of F as a morphism between these 2 projective varieties. Now everything happens on those surfaces, so you can easily calculate the intersection numbers of exception divisor and transformations. So we might have result using some projection formula of your intersections. So we might calculate these intersection numbers like this. And if you have product of H, just claim everything has coefficient A, B, and C. Then, using previous intersection numbers, you can calculate what the A, B, and C is. So you can exactly find your two product of H by your reserved morphism and by rational maps. Now I define your D ratio is derivable original map times maximum ratio between your coefficient, which is half, 1, and 1. So your maximum value is number 1. So you have D ratio like number 2. Here's another example, which is quite a famous example in arithmetic dynamics. Just let me say we have such maps. Then that's the famous map named Hidden maps. That's regular polynomial holomorphism. That has inverse map on affine space. But in terms of projective space, it's rational map because they are not well defined on some points like 1, 0, and zeros. If you say your polynomial is of degree D, then we need 2 to the minus 1 blow-ups like this. First start with your H, then make a blow-up on E1s, and blow with intersection of H and E1s to make E2, and another blow requires, which comes from intersection of E1 and E2, and so on. And we requires D blow-ups here and there, and we need another D-1 blow-up, which has some points on affines. So we need the 2D- blow-ups to resolve your hidden maps. Once we program like this, we can exactly find the representation of your proved by violation map and proved by resolved morphism. So we can calculate what your D ratio is. D ratio comes from degree of original maps and maximum of your ratios, which comes from 1 over D and I over D and D over Di minus J's. So maximum happens when your D is D minus 1. So you have D ratio as square of your degrees. If you have regular polynomial holomorphism higher dimensions, then the situation is more complicated. if we have blow on surface, we only have blow along a point, so calculating the blow is quite easy. However, if you have P3, P4, and so on, you should blow along curves, some surface, and so on. So this blow is so complicated, so I cannot show you what the picture is, but we can say it like this. Just we choose a regular polynomial homomorphism, then we can find a resolution of indeterminacy. Then your two product is generated by basis of Picard V. Then always coefficient of H pi comes with 1 and degree of your map, and exceptional part has AI and BI coefficients. Then your D ratio is always not greater than your degree of inverse map. Actually, if you have a Hannon map on affine two spaces, then your map and inverse map should have same degrees. But if you have a regular polynomial homomorphism on higher dimensions, this map and this inverse map might have different degrees. So their D ratio comes from maximum part, which is called essential part, which is not shrink by push forward by reserved morphisms. Then we exactly find coefficient of essential divisors and other ones. So we might claim your D ratio is multiplication of degree of original maps and degree of the inverse maps. Now we have main result like this. Just let me assume we have polynomial maps whose D ratio are given. Then we have weak Northcott probability, which comes from D ratio over degree of F. That's not surprising things because I said D ratio is constant, which makes difference of your pullback by reserved morphism times this quantity minus pullback by your bidirectional map is affine effective. So we have affine effective divisor. So corresponding height is bounded below on affine space. So we have height corresponding to your affine effective divisor. So that's bounded below. And is composition of this constant times pullback minus pullback by bidirectional maps. So by fact, we have homomorphism between your Picard and height functions, so we can decompose it like that. Once we decompose it like that, by functorial probability, because we have morphisms, not relational map, so we can change your height function like this. Now, from the fact we have two bidirectional maps like this, so change everything with polynomial map notations. So we have original point and image by your rational maps, and this quantity is bounded below. So we have this constant, this coefficient times height of image is greater than height of points. So we have good relation between height of point and height of images. So we can generalize some theorem from morphism cases. Just let me define a set of prepared points where some iterations of f and iterations of other iterations of f has same image by p. Then we say that's the point that p is prepared points of given rational maps. And in morphism case, Northcott probability plus consequence result named canonical heights, we might say your prepared points is saddle bounded height, which says we only have k rational prepared point are finite many. We might generate these results like this. If you have a rational map whose D ratio is greater than smaller than its degree, then we might say your prepared point is a saddle bounded height, so we only have k rational points finite many. For example, if we have morphism, you have number 1. So if you have morphism of degree n is 2, it satisfies this inequality, so we can easily induce the morphism case. In rational map case, we have some unclear restriction, like you have d ratio smaller than degree, but still we have result on arithmetic dynamics. Skew is quite the same with the morphism case. If you have d ratio smaller than degree, then first one, your d ratio generates height inequality like this. So we might use some telescoping sums. So if you repeat these iterations, then, previously we have some relation between d ratio of compositions and multiplications of d ratios. That gave, we have iterations like this, so we can reduce powers of your maps. So finally, we have such inequalities. If you have fn iterations image times n power of your d ratio of degree, then that will bind your height of p plus some finite constant. Because we assume this number is smaller than 1, so near infinity sum is always bounded. So we have two inequality with finite constant. So we have these inequalities. If you send your n should go infinity, not f. If your n goes infinity, then this quantity O is always bounded below by this constant. So if you assume you have prepared points, which means you have only finite many choice for your n iteration points, so they are always bounded, and you have power of number smaller than 1, so your left hand side goes 0, so your height of points is bounded by this constant. Which means if you have any prepared points whose height is always bounded this constant, therefore set of prepared points is of bounded heights. Now, just using height property, which says if you have set of k-rational point, which is of bounded height, then you only have finite many. So we only have finite many k-rational point for such rational maps. And here's some clear corollary. If you have some number which satisfies your iterations d ratio is smaller than the degree of your iterations, then still prepared points is a bounded height. Because if you have iterations of f, it should have same prepared points of original maps. Here's an example. Let me give you a polynomial map defined by x cubed plus y and y squared plus x. Then it requires grid roll-ups to resolve indeterminacy. And after grid roll-ups and with the same scheme, calculating all intersection numbers and compare your coefficient with your compositions, then you have this result. You have two proof-x, which is represented by basis of your Picard width. Then comparing your coefficient and multiplying your degree, then you can calculate your d ratio is 2. Then in this case, we have degree maps. So you have d ratio smaller than degree of your map. So its prepared points is of bounded height. Here's another application. For example, just let me say we have a polynomial map such that your d ratio is smaller than its degree. Then we can easily check your period point is Jarsky dense in projective space because they're Jarsky dense in affine spaces. If you check Vaccarini's result in 2005, he proved when your envelope is 1, which means we have morphism case. If we have morphism case, then that is proved by Vaccarini. It requires lots of complicated theory like some model theories and some higher level of geometries. So here's simplified versions. If we have polynomial map such that D ratio is smaller than degree of f, then it says your k rational periodic points is finitely many. Which means if we choose some k and choose k periodic points, which means if you iterate your kp times, then that fixes your p's. Then it's always discrete whatever your base field is. Which means if you have rational map like that, as an actual rational map, now we consider is integral models. Now we observe this one on each special fibers, and we have generic fiber here. Now observe on each special fibers. Then k-periodic point is always discrete on almost all special fibers, and check what's your k-periodic points on integral models. Now, it says it cannot be of dimension 0 because it has infinitely many intersections on special fibers. So your k-periodic points is actually finite union of horizontal sections. Now, observe your periodic points. Then, any special fibers, their finite extension is always finite field. So, periodic points on each special fiber is everything. So, if we union, if you make union of all horizontal sections comes from k periodic points, then their intersection with any special fiber is everything. So that guarantees on generic fibers, their intersection should be just dense. So that says if we satisfy this inequality, it gives you the same result with Morrison case. Actually, that sounds like, okay, just dense, that's good, but it gives you some other applications. For example, just let me give you one example like this. If you remember, if you have polynomial of one variable, two polynomials are commuting if and only if they are power of some same polynomials or Chebyshev polynomials or power maps. We might have almost similar results like this if we have a fixed affine maps which satisfy that conditions. Then you might have finitely many maps of fixed degree which commute with given maps. So even we just say we have just dense periodic points, that give you some finite probability which comes from commuting maps. So that's quite interesting result on arithmetic dynamics. Oh, I made some slide like this. Previously we just say if we have set of maps which is commuting with first maps, I just forgot your degree is D, then that's a finite set.
Sorry, G.
Yes.
Polynomial on A to the n.
A to the n to A to the n.
So G is a rational map on P to the n. So that's
Yeah, you might say the extended like just we have rational maps, but I just give you the we have polynomial map case.
Okay, great. Thanks.
This D ratio gives you another applications. Just let me say I have finite family of rational maps, and I call this family as jointly regular if they didn't have common indeterminate points. If you choose any point, at least one map is defined at the point. Then, Simon's results in 2006 says, I don't know what's the D ratio of each maps, but if you make sum of height of images divided by degree, then that becomes another upper bound of height of points. So previously, weak Northcott property says I just make upper bound of H of P by some multiple of height of image by one maps. But if we have some special kind of maps, we might have another kinds of upper bounds which comes from some composition of height of image by family of maps. Here's another example. If we have geometry regular polynomial holomorphism, like hidden map we saw on previous slides, then there's a result which made by me and Kawaguchi independently, just the 3-day gaps. Now we have result like this. If you have height of points divided by degree and height by inverse image and divided by degree of inverse maps, then will bounds your height times some bigger number. So that's little improved compared with C1C1s. C1C1 says if you have such compositions that only bounds height of points. But if you have regular polynomial holomorphism case, we slightly improve your upper bound by this constant. Because if you divide the bounds and side with this number, which is greater than 1, so we have little smaller upper bound compared with the Silverman's theorems. But it's quite a strong one because that is enough to define canonical heights for regular polynomial holomorphisms. Previously, we have some weak Northcott property for your rational maps, but that's not enough to claim we have canonical heights for rational maps, because that upper bound does not guarantee sorry. If you have point whose height increase slower than expected, then previous telescoping sum says this point has a bounded height. But so it's not enough to claim we have canonical heights there, but this inequality is strong enough to claim we have canonical heights for regular polynomial holomorphisms. And here's one more improved result. Yeah. Similar result says we have this result here. Now we can introduce one more, not only in the regular polynomial holomorphism case, but all kinds of rational map case. If you have rational map like this, then composition of height of image by your family will bounds your height of point times some number greater than or equals to 1. That generalized the theorem of Silverman. He showed if we have D like this, then it says we have common periodic points made by all possible compositions of your Fs. Now I will generalize a little more to make your D, which is little bit smaller than expected. Now we can have your common periodic point, which is made by monoid of your finite maps, then that has finite bounded height prepared points. Yeah, we have the family of finite maps. Then we have all possible compositions of F1 and Fms. We might have just iterations of Fi's and F1, F2, F1, F2, and so on. So we consider all possible combinations of your finitely many maps. And we say that's the monoid generated by this S. Then it says if we have point which is periodic for all possible combinations, then we say that's periodic by this monoid. So actually that's not quite useful in some sense, but if we assume we have set of finite maps which are commuting each other, then they will share same periodic points. So actually that says we have periodic points of one maps. That's the exact case with regular polynomial holomorphism. If you have F and F inverse, then we have family of two maps their composition is nothing but F iteration, so F inverses iterations, and they will have same period points for any iterations, so that's actually period points of one map. That's everything, I believe. And actually, I tried to introduce some questions induced by my research, but yeah, we didn't have much time, so I should be stop here.